We're going to finish off our chats about probability distributions with the geometric and binomial distributions, which are specific models for determining the probability of finding a certain percentage of objects within a larger group, or how long you have to wait until you find a particular type of person or thing. So we're going to start with the geometric distribution question, and we're going to start by talking about people who are not in grade 9. So if I'm doing a geometric question, the thing I'm asking myself is, how long am I going to have to look until I find someone who is not in grade 9? So if I have a 75% chance that someone is not in grade 9, that should make sense, because a typical high school has kids in grades 9, 10, 11, and 12. That's 4 different grades, and only one of them is grade 9, so it's about 25%. If I wondered what the probability of the first person I asked not being in grade 9, well, that's easy. That's just 75%. So first person, 75%. But if I couldn't find someone not in grade 9 until the second person I asked, you kind of have to put this in context. If I'm waiting to the second person to find someone not in grade 9, that means the first person must have been in grade 9. So for this scenario, I walked up to a random bunch of people in the cafeteria and I grabbed one and said, "Are you not in grade 9? And they said, "Oh God, yes, I am in grade 9, sorry." It's like, okay, fine. And then I went to the next person, and that person was not in grade 9. So what had to have happened here is that I found someone who was in grade 9, 25% chance of that happening, and then found someone who was not on my second try. The next scenario, so I either find this non-grade 9, the first person I ask, or the second person I ask, or maybe it's the third person I ask. But in order for this scenario to have unfolded, I had to speak to one person who was a grade 9, a second person who was a grade 9, and only on the third did I find someone who was not. So that would be 0.25 for the first grade 9, then another for the second grade 9, and then another who is not in grade 9. Just to make sure this pattern is completely clear, if I don't find a non-grade 9 until the fourth person, then the first person I asked was a grade 9, 0.25. The second person I asked was a grade 9, 0.25. So was the third, 0.25. And only the fourth person was not in grade 9. So as I'm going up through this list, the further down I go, the more grade 9s I had to find first before identifying the first person who is not a grade 9. So I'm going to take this and I'm going to put it into a chart. So x, that'll be the variable, that's going to be the ranking of the person I find who's not a grade 9. Is it the first person? Is it the second? First. Is it the second? The third? The fourth? The fifth? The sixth? The seventh? The eighth? The ninth? Etc. So if I were to put these numbers here into this chart, the probability of finding that grade 9 or the not grade 9 on the first go is 0.75. The probability of finding a not grade 9 on the second try means I had to have found 1 grade 9 before I found the type of person I was hunting for. If I find that person on the third try, it means I must have stumbled across 2 grade 9s. Notice I've used squared here. This times this is the same as 0.25 squared. Makes it a little shorter to write, especially when I get into these longer lines. 0.75. If I find this person on the fourth time, I must have had to find 3 grade 9s first. Or maybe I found 4 grade 9s first. Or maybe I found 5 grade 9s first. You see how this goes. Now, I'm going to keep drawing this list because there's a point I need to make to you, and I'm going to need many rows to do it. Generally, we stop making these charts after the 5th or 6th row, because these probabilities are going to shrink down to almost nothing as we get deeper. And if you think about that, it's not hard to find somebody who's not in grade 9. It's not hard to stumble into a grade 9 first and then find someone who's not in grade 9. But it would be strange if you walked blindfolded into the cafeteria and found a grade 9, then 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 a grade 9, before finding someone who was not. There's just not enough of them for that to be plausible. But that is what this row is here. Right? Stumbling into 8 grade 9s before you find someone who is not. And when I actually calculate these decimals, we should see the sort of diminishing return as we get down there. So I'm just going to erase this so that we have some space. There's a little gap here, and I left that gap tactically. I can fill that in. 0.25. How many grade 9s did I find here? Well, I didn't find any. And if you check your exponent laws from grade 11, then any number to the exponent 0 just is 1. So if you're multiplying by 1, it doesn't matter. Check that with your calculator. So I'm going to go through and I'm going to actually do these calculations. I'm going to flip into fast forward mode at some point so that we can just get through it more quickly. Basically, the first one, 0.25 to the exponent 0 is 1. Multiplied by 0.75 gives me 0.75. This next row, 0.25 multiplied by 0.75. Let's try that again. 0.25 times 0.75. 75 is 0.1875. And look what's happened to that probability. There is quite a drop from this outcome to that outcome. For this one, 0.25 squared is 0.0625 multiplied by 0.75 is 0.046875. And I'm going to cut it off at 4 decimal points. 0.0469 if I round. This row here, 0.25 cubed times 0.25 times 0.25 is 0.15625 multiplied by 0.75. I'm having some calculator rage right now. 0.25 times 0.25 times 0.25. 0.15625 multiplied by 0.75 is 0.1171875. If I round it to 4 decimal places, I'm at 0.0117. Now, if you notice, something that will speed this up for you, the only difference between this number and this number is that I multiply by 0.25 an extra time. So to get to the next row, you're really just taking this number and multiplying it by 0.25. Then you take this number and multiply it by 0.25. And then you take this number and multiply it by 0.25, etc., 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 down the chart. So I'm just going to do that so we can get to the end. Times 0.25 is 0.0029 times 0.25, 0.0007 times 0.25 is 0.00018. I'm going to round that to 2 times 0.25 is 0.00005. And one more time, just because I've drawn the chart already, 0.00001. All right. So as you can see as I go down here, the probability of wandering into the cafeteria and blindly choosing person after person after person and getting 8 grade 9s in a row before you found someone who was not a grade 9 is getting pretty hard to do, right? That's 0.001%. So that's bordering on statistically impossible. So you can see that sort of dropping as we go. The last thing I need to ask is what is the expectation? Right, so how long would I have to wait? How many people do I expect to ask? Before I find someone who is not in grade 9. Well, we've done expectation values when we were doing the games of chance. And so the way you did that is you took the probability of an event happening and multiplying it by the value at which happens. Now in the games we were doing it this times the prize, because the prize is really all you cared about. In this particular question, it's this number, right? Did it happen on the first person? Did it happen on the second person? So there's a probability of 0.029 that it's the 5th person you ask is the first one you find who's not in grade 9. So I'm going to make my expectation column by taking how many people I had to ask multiplied by the probability that it was that many people. So 1 times 0.75 is 0.75. 2 times 1.1875 is 2 times 0.1875. 0.375. And then 3 times 0.0469. 3 times 0.0469 is 0.1407. 4 times 0.0117. 0.0468. 5 times 0.0029. 0.0029. 0.145. 6 times 0.0007. 0.0042. 7 times 0.0002. 0.0014. And 8 times this would be 8 times 0.1, 4 zeros and a 5. It's 0.0004. And 9 times this one. 9 times 0.1, 2, 3, 4 zeros and a 1 is 0.00009, which I'm going to round to 0.001 because I'm only keeping 4 decimal points. Okay, so when we were doing expectation values for games, you had to take the amount that you budgeted here plus the amount that you budgeted here plus the amount you budgeted here, and you had to add them all up. So I'm going to do the same thing. I'm going to take 0.75 and I'm going to add 0.375 and I'm going to add 0.1407 and then I'm going to add 0.0468 and then I'm going to add 0.0145. Then I'm going to add 0.0042 and 0.0014 and 0.0001. I'm going to get 1.3327. All right. Now you might have noticed that this chart isn't done. I mean, it is technically possible that you could find 9 grade 9s and then the person you're after, or 10 grade 9s, or 11, or 12. Technically, this list goes forever. Now, if you're in the cafeteria at your particular high school, eventually you run out of grade 9s, and that is a limitation of the model. But if you were doing something that wasn't quite so finite, like you were digging through water molecules and like Huron hunting for a heavy water molecule, there are a lot of those, and you would likely lose interest before you ran out of water molecules to check. So this chart technically never ends, which means that this answer here is only an approximation, because I have to add up all these values for an infinitely long chart. Now I have better things to do with my time, and so do you. Because you notice that once I got to here, and this is only the 9th row, the amount I'm adding to this is way down here. It's all the way down in the 10,000th place on this digit. So my answer is going to be pretty close to 1.33. Now that's a funny number, 1.33. That's awfully close to 1.33333 repeated, which happens to be 4/3. Now if you take a look up here into our starting information, 75% of my people, that's 3/4, are not in grade 9. So it looks like the expectation value is this fraction, but flipped. So if I were to write that for you as an equation then, or as a relationship, I'm gonna erase this and I'm gonna do some summarizing for you, and then we'll come back to that. So if I summarize that for you, a geometric distribution is useful, right? This model applies anytime you are hunting for a specific object or type of person, and that you're going to keep asking people until you find one of those. So this is, perhaps you've heard the colloquialism, your keys are always in the last place you look. Well, obviously, because once you find them, you stop looking. So your keys are always in the last place you look. But the point of that little colloquialism is that you kept hunting until you found your keys. So what's the probability that you find your keys in the first place you look? What's the probability that you find them in the second place you look? Because you're going to keep looking in places until you get your keys. And if that's the activity that you're doing, you are following a geometric distribution. So if you were to reach blindly into your cookie jar and keep pulling out cookies until you found a chocolate chip one, that's a geometric distribution. Because as soon as you get your delicious chocolate chip one, you stop and you leave, leaving all the disgusting raisin nonsense all over the counter. So if that's what you're doing, a geometric distribution is for the behavior of hunting until you find what you're looking for. And if that's the case, the expectation value for this distribution is 1 over the probability of finding the thing that you're after. So if you were trying to hunt for, let's say, left-handed people, you're going to walk through the room until you find a left-hander. The probability of a person being left-handed is about 15%. So the expectation for a left-hander would be 1 over 15%, 0.15. So if I do that, 1 divided by 0.05, 1 divided by 0.15 is 6.667. So I would expect at a 15% probability of a person being left-handed that I wouldn't find one until the 6th person I asked. If it took me longer than that, something curious is going on, because I should have found a left-handed person by now. If it takes me less than that, something curious is going on, because I shouldn't have found a left-hander so quickly. That's sort of how this works. If you were going through a room of random people, and you ask them, are you left-handed? Yes or no. Are you left-handed? Yes or no. And you keep going until you find someone who's left-handed. That's hunting until you find one. And you would expect to ask 1 over 15%, which is 6.667 people, before you found one. So we're going to take this, I'm going to get this out of the way, and I'm going to ask a few questions about probabilities of finding people. So this is how these questions work. I've generated this table, and then I need to acknowledge that this table does in fact go on to infinity. It never stops because it's a geometric distribution. Once I've developed this chart, 5 or 6 rows of it, I'm going to be asked a question like this. What is the probability of finding a non-grade 9 for the first time? And this is the phrase here that triggers geometric distribution, right? This phrasing implies that I keep asking people until I find a non-grade 9 for the first time. What's the probability of finding a non-grade 9 for the first time on the 3rd person? Well, 3rd person, there it is. The answer to that is 0.0469. I just had to pluck the row out of the table. The next type of question you might be asked is, what is the probability of finding a non-grade 9 for the first time in less than three people? So notice this was on the third person, and this is in less than 3 people. So less than 3 people would be the first person you ask or the second person you ask. So if I look at that in the table, it could happen this way or it could happen this way. So when you say that word or, it means you have to add those probabilities together. So the probability of finding someone in less than 3 would be 0.75% that you find them on the first try, or 0.1875 that you find them in the second try. And if I add those together, 0.75 times 0.1875, it's not that, 0.75 times, no, plus 0.1875 is 0.9375. So if you walk into the cafeteria and you start asking people at random to find someone who is not in grade 9, you have a 93.75% chance of finding someone who is not a grade 9 in less than 3 people. Perhaps you can intuit what the next type of question was. What is the probability of finding a non-grade 9 for the first time in more than 4? So what is the probability that it takes you more than 4 tries in order to find someone who is not in grade 9? Now that's a tricky one for this table, because more than 4 would be this row, and the 6th, and the 7th, and the 8th, and the 9th, which I've erased. But it also includes the 10th, 11th, 12th, 13th, etc., all the way to infinity. Well, that's no good, because I don't want to make an infinitely long table. We've said this before. You have better things to do with your day than write this table forever. So we're going to be a little tactical about it. If I'm asking a question about more than 4 people, that means it's every row except this one, this one, this one, and this one. So if I add all these rows up, I should get 100%. But I don't want this row, because finding them on the 4th person is not more than 4 people. I don't want this row. I'm going to take it out, because finding it on my 3rd person is not more than 4. I'm going to take this one out, and I'm going to have to take this one out. Because finding someone on the first try is not more than 4 people either. So, forgive me while I swear at this calculator for a little longer. 100% minus 0.0117 minus 0.0469 minus 0.1875 minus 0.75 leaves me with 0.0039. So there's a 0.39% chance of it taking more than 4 people. Now, that's a neat little answer, because there are an infinite number of rows here. So if you started typing in these numbers, right, this row plus this row plus this row plus this row, you would never finish, because there's an infinite number of them. There is no end to that list, so you would be typing into your calculator forever. But if you did, if you took forever to add all those numbers together, that's what they'd add to. So this idea that an infinitely long list of numbers has a finite sum that's a very peculiar outcome, right? You shouldn't be able to add an infinite number of things and get an exact value at the end, especially not one that small or that tightly defined. But that idea is sort of fundamental to calculus, and it's fundamental to probability and statistics in that if you have a set big enough, sometimes that set will actually whittle its way down into a nice tightly defined number, which is sort of neat to think about. All right, so we've done expectation for a geometric distribution, and we've done questions like this: on the third person, less than 3 people, more than 4 people. The other one you have to watch is the phrase at least. So if I say at least 2, that means 2 is okay, and 3, and 4, and 5. More than 2 is 2 doesn't count. So in this case, more than 4 people, I threw away everything that was 4 or less. If I had said at least 4 people, then I would have had to throw away 3, 2, and 1. All right, so we're going to do the same question, but in a binomial kind of way. So we're still hunting for people who are in grade 9 and for people who are not. And I'm going to have to erase the board for some space, so let's do that. All right, the difference between the geometric distribution and the binomial distribution is geometric, you keep hunting until you find one. A binomial is I'm going to set how many people I'm going to ask, and then I'm going to count how many of them actually meet this criteria. So if I'm hunting for people who are not in grade 9, and I'm going to ask 5 people, then the outcomes are as follows. Maybe none of them are not in grade 9. Maybe one of them is not in grade 9. Maybe 2 of them are not in grade 9. Maybe 3 of them are not in grade 9. Maybe 4 are not in grade 9. And maybe 5, maybe all 5 of them are not in grade 9. So those are my options. It's quite a squeal this marker makes on the plastic. Now, to calculate the probabilities, if none of my people are not in grade 9, that means that all of them are in grade 9. Right? These things are mutually exclusive. So I must have five grade 9s and no, let's call them senior students just to save the confusion. If I find only one senior student, that means in my group of 5 people, 4 of them must have been in grade 9 and only 1 was a senior. If I find 2 people that are not in grade 9, then 3 of the 5 people I asked must be in grade 9 and 2 are not. If I find 3 people not in grade 9, that means the balance of 2 people had to be grade 9s. Four means there's only 1 grade 9 and 4 people who are not. And if I find 5 people not in grade 9, then none of them are in grade 9 and they're all in this pile here. Lovely. Okay. So, if I were to go through and actually do these multiplications, 0.25 to the exponent 5, let's see, 0.25 to the exponent 5 times 0.75 to the exponent 0 is 0.00097. So I'm going to round that to 0.00. I'll just keep 5 digits for this one. 098. if I were to go and do this row, 0.25 to the exponent 4, 0.25 to the exponent 4, multiplied by 0.75 is 0.00293. The next row, 0.25 cubed times 0.75 squared is 0.00879. The next row, 0.25 squared times 0.75 to the exponent 3 is 0.02637. And 0.25 times 0.75 to the exponent 4 is 0.07910. And my last row, 0.25 to the exponent 0 multiplied by 0.75 to the exponent 5 gives me 0.23730. Now if you were to look at these numbers and think about what's happened, I grabbed 5 people and I'm trying to figure out how many of them are in grade 9 and how many of them are not. If you think about the possibilities, if you grab 5 people, either 5 of them are in grade 9, 5 of them are in grade 9, 4 of them are in grade 9, 3 of them are in grade 9, 2 of them are in grade 9, 1 of them is grade 9, or none of them are in grade 9. There aren't any other options. So I've covered everything. This chart does not go on forever, right? The next row would be 6. What's the probability of 6 of your 5 people being not in grade 9? Well, you can't have 6 out of 5. So this chart is done, which means these probabilities should add to 100% chance. And they don't. That's 23. That's about 8. So we'll call that 24. That's about 8. So we're at 32. Call that 3. We're at 35. That's less than 1. We're at 36. And oops. We're a little shy. So there's a number here missing. You notice I've left a gap. Tactically, as always, left a gap there for something that we need to fill in still. So this part's a little hard to wrap your brain around. So the thing is, if I had 4 grade 9s and 1 person who's not a grade 9, so let's see. I might have found my not a grade 9 first, and then found 4 grade 9s. This is not a geometric distribution. I didn't stop when I found them. I just found 5 random people and asked, and maybe that's the non-grade 9, or maybe that's the non-grade 9, or maybe this is the non-grade 9, or maybe this is the non-grade 9, or maybe it's not until the last one. So that non-grade 9, right, that one person who is not a grade 9 could be here, or here, or here, or here, or here. That means that there are 5 possible positions that that person could have been in. This one here, where they're all grade 9s, well, there's only one way to write that. He's a 9, he's a 9, he's a 9, he's a 9, he's a 9. There's only one way to write that out. So there's only one way for this one to occur. For this one, I've only got 3 9s and 2 non-9s. So they could have been, Oh goodness. They could have been like this. They could have been like this. I'm just going to erase all of these. They could have been like this. Oh, hang on a second. Sorry for the hard cut. What are we doing? Right. That non-grade 9, they could have been stacked beside each other. Or it could have been like this. Or it could have been like this. Or like this. Well, that's all the options where there's a non-9 in front. So maybe a non, and then maybe like this. And then like this. And then like this. That's all of them where they're in the second position. So how about 9, a 9, a non, a non, and a 9, a 9, a 9, a non, a 9, a non. If you're listening to me prattle on in the library, talking to myself about this, talking about 9s and nons and nons and 9s, it sounds really ridiculous. So rest assured, I haven't lost my mind. I'm just counting in an organized fashion. Last one, 9, 9, 9, non, non. Whew, there we go. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different ways I could sort these non-grade 9s and grade 9s. So I'm going to need a 10 in front of this one. Now, I don't want to do this anymore. But if you can imagine in this row, every place, instead of 2 non-9s and 3 9s, I would have 3 non-9s and 2 9s. So everything that's a blue N would become a pink 9, and everything that's a pink 9 would become a blue N. In all of these different combinations, which would still lead to 10 different sortings. This one here, 1 grade 9 and 4 nons. Well, that grade 9 could have been in first position, second position, third position, fourth position, or fifth position. That's it. Total of 5. And there's only one way to draw 5 blue ends. Like that. And you notice the pattern went up and down symmetrically. I'm going to erase this mess here. We're going to fix these numbers because they're not quite right. This value here was okay because it's that multiplied by 1. That's not going to cause a change. But this one should have been multiplied by 5. So let's try that. 0.00293 multiplied by 5 gives me 0.01465. This row here should have been multiplied by 10 because there were 10 different sortings of these people. So 0.00879 times 10 gives me 0.0879. This one here, 0.02637 multiplied by 10 would be 0.2637. This row should have been multiplied by 5 for the 5 sortings. So 0.0791 multiplied by 5 gives me 0.3955. Now that I've corrected this, just to prove that this is the right thing to do, if I add this plus this plus this plus this plus this plus this, I should get 100%. So I'm going to give that a try. 0.2373 plus 0.3955 is, that's 63%, plus 0.2637 is 89%, plus 0.0879 is 98.4%, plus 0.01465 is 99.905%, plus 0.00098 gives me 1. Almost right on the nose. There's a bit of a rounding error, but it's pretty close. So I need these numbers in front in order to adjust these probabilities up for all of the sortings of how those people appear. So here's my distribution table. I am going to circle back to these numbers and what they mean and where they come from after I do a little bit of work on this distribution. So patience. So we're going to have to ask those same questions that you were asked in the last distribution. What's the expectation value? And then what's the probability of finding this many or more than this or less than this? So if we try to do expectation values were the probability of something happening multiplied by the number of things you get for it. So if I'm hunting for non-grade 9 students, there's a 0.00098 probability multiplied by 0 gives me 0. A 0.01465 multiplied by 1 gives me 0.01465. 2 multiplied by this would be 2 times 0.0879 gives me 0.1758. 3 times 0.2637 gives me 0.7911. 4 times 0.3955 gives me 3.6045. And 5 no, that's, I think I hit subtract, not multiply on that. Let's try that again. 4 times 0.3955, that's better. It's 1.582. And then 5 times 0.2373 gives me 1.1715. All right. Now to get an expectation value, I'm supposed to take all of these rows and add them up. And I don't have the problem last time where the table was infinite. I only have to add these 6 numbers. 5 actually, because adding 0 doesn't change anything. So 1.715 plus 1.582 plus 0.7911 plus 0.1758 plus 0.01465 gives me 3.735. Non-grade 9s. All right. Okay. Now, if you were to think about that, though, if 3/4 of people are not grade 9s, and I ask 5 people, then 3/4 of those 5 people should not be in grade 9. Well, 3/4 of 5 is 15/4, and 15 divided by 4 is 3.75. So I have a little bit of a rounding error here, but instead of doing all that work to get the expectation value, I could have just used Manergan and realized that 3/4 of 5 people is 3.75. So if you ask 5 people and 3/4 of them should not be in grade 9, I would expect 3.75 of them to not be in grade 9. Now again, these decimals for people, I know that doesn't make sense. We're not supposed to be using these distributions on groups of 5. We're supposed to be using them on groups of 5,000. So put 3 zeros on the end of that, and suddenly this becomes 3,750, and which makes more sense. I just didn't want to make a chart with 5,000 rows in it, and neither do you, so you're welcome. So that's it. I'm going to shorten this up though. You notice that this is the probability of finding the thing I wanted, and this is the number of people I asked. So I could summarize this for you just like the geometric. I'm going to erase this and I'm going to do that, and then we'll chat about it. So the binomial distribution is used to model a situation where you decide in advance how many people or how many objects you're going to sample. In this case, it was 5. And once you've decided how many you're going to check, all you're doing is counting how many of those meet the criteria you're after. So in the other example, the geometric series, the cookie jar problem was, I'm going to take off the lid and I'm going to keep throwing cookies in the garbage until I get the chocolate chip cookie I want. In a binomial way, I would dump 8 cookies on the counter and then see how many of them were chocolate chip. So if you're doing it that way and you're deciding you're going to ask this many people and it's either all of them, none of them, or some number in between, you're doing a binomial distribution and you model it this way. If that model applies, then the way you calculate your expectation value is to just take the number of things that you're going to check and multiply it by the probability of them meeting the criteria you're after. So now that I have the model built, what is the probability that out of 5 random people, 3 are grade 9s? Oh, 3 are not grade 9s. Okay, well that was this row in the chart. That's 3 people not in grade 9, so the probability of that should be 0.2637. That's pretty straightforward. Just like the geometric ones, we're just finding rows in the chart and then picking out the rows that we like. So question B, what is the probability that out of 5 random people, at least 4 are not in grade 9? Well, at least 4 means 4 or 5. That will do. So the probability for 4 of them is 0.395. And I'd have to add to that the probability of there being 5 is 0.23730. For a total of 0.3955 plus 0.2373 is 0.6328. So there's a 63.28% chance that at least 4 of them are not in grade 9. So those questions are very similar to what you asked in geometric. The trick then is being able to identify whether a question is prompting you to use geometric or is prompting you to use binomial. So the words you're hunting for are out of. So this question, which was binomial, said, what's the probability that at least 4 out of 5 are not in grade 9? By saying out of 5, you are implying that I have pre-decided how many people I'm going to ask. And as soon as you've done that, as soon as you set a small chunk for your sample, then that's a binomial question. if the question had said, keep going until you find one, that's a geometric question. So try and keep that in your head when you're doing the problems, the practice problems, is trying to hunt and figure out which one's which. I would like to cycle back and talk about what these numbers are and where they came from, so I'm going to clear up some space so we can do that. So you may have come across a thing called Pascal's triangle, just as like a little math fact, somewhere in your elementary school time. And Pascal's triangle is just a neat little pattern. You start with 1, and then you start with 1 like this, so it's like the corners of a triangle. Now I'm going to add a row to this triangle. So I'm going to add a row on the outside, and a row on the outside. And you notice that this location here is located under this one and this one? Well, 1 and 1 is 2. If I were to add another row to this, 1, 1 on the outsides, this location is between a 1 and a 2. 1 plus 2 is 3. 2 plus 1 is 3. If I keep adding rows, a 1 on this side, a 1 on that side, 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4. Add another row, 1 on the outside, 1 on the outside, 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5. Now, if you go back into where we were doing the binomial distribution question a minute ago, the coefficients that were down this side were 1, 5, 10, 10, 5, 1. And I generated those by finding all the different positions I could sort those grade 9s and non-grade 9s into. I didn't have to do that. I could have just grabbed a row of Pascal's triangle, which is super handy. So you should make an effort to find one of these, or to have one printed and sitting in your binder when you start to do these binomial questions, and certainly when we get to the next unit when we do counting theory, because these numbers and the sequence of numbers keeps coming up again and again and again. So I'm going to add a few more rows just so we have some fun things to work with. 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and then there's a 1 on the outside. Okay. So when you're doing a binomial question, I'm just going to write one down. I'll do it in fast forward mode so we don't have to get stuck on it. All right. So in the last geometric question, to try and give another example, I talked about left-handedness. So about 15% of people are left-handed. So if I were to ask 6 people, what is the probability that 2 of them are left-handed? Now that's binomial, because I'm going to ask 6 people. I'm not going to keep asking until I find one. I'm going to ask 6. So if I were to make this chart for the distribution, I would need to have, well, none of them are left-handed. 1 is left-handed, 2 is left-handed, 3, 4, 5, or all 6 are left-handed. That's 7 rows. Did you notice that this row here with the 6 in it has 1, 2, 3, 4, 5, 6, 7 rows. It's perfect. So if I were to build that chart, I'm going to erase this up here and use the space. Just quickly building the chart for this distribution, no left-handers, 1 left-hander, 2, 3, 4, 5, or all 6 are left-handed. I'm going to need to map these coefficients into the beginning of each of these categories. So 1, 6, 15, 20, 15, 6, 1. If there are no people who are left-handed, that means this 1 here is multiplied by 15%, showing up 0 times. and 15% are left-handed, then 85% are not. So there are none of these folks and 6 of these. In this row, there's 1 of this type of person, so there must only be 5 of this type. This row, there are 2 of this type of person, so there must only be 4 of those type. This is much faster than what we did before. It's the same thing as we did before, but I know the pattern in advance now. So I just have to jot these numbers in and then quickly calculate the values of each row. 0.15 squared, 0.85. Oop, nope, that's 5. 1. And this would be the probability that they're all left-handed. Alright. Now the question asks, what is the probability that 2 of them are left-handed? Exactly 2. So that would be this row. So if I were to pluck that out of there, 0.15 squared times 0.85 to the exponent 4 times 15, don't be doing that, times 15 is 0.1762 if I round. So there's a 17.62% chance that exactly 2 of them are left-handed. How many would you expect? Well, it's binomial, so the expectation of left-handers would be the number of people I ask multiplied by the probability of finding one. In this particular question, I asked 6 people, and there's a 15% chance of finding one. So 6 times 0.15, it's not that, 6 times 0.15 is 0.9. So I would expect to find 0.9 of a person who's left-handed. And again, we're not supposed to be using this on groups of 6. We're supposed to be using it on groups of 6,000. So out of 6,000, you would expect to find 900 left-handers. But this is just the mechanics of how it works.